Thank you very much, Professor Groupie, making me a professor, but I'm not so. Thank you very much. So, I will talk about measurement of dissipated energy by logging thermography and heat flow measurement. The heat flow measurement is a method which was introduced by the group of Oleg Bekov and Alexei Vyshkov. It's Russian, so it's hard for me. They were in Munich 2 years ago and introduced this method to us. We made some measurements, we made some improvements, and now I will show you these two methods in comparison to see where are the advantages and where are the limits of these methods. I will talk about experimental details, which I can make very short because you have seen everything in the presentation before. In the crack propagation experiments, it's where the same crack propagation experiments you've already seen. Logging thermography, I think I don't have to say anything about that because the last two presentations have explained everything very well. But then the heat flow measurements, I think it's new for most of you. So I will spend some words on the sensor we use and how it measures. And then I will show you the results and compare these two methods and will show you where there is the problem with the heat flow measurement in comparison to the thermography. Okay, and ending will be with a short summary. Good, crack propagation experiments, you've already seen our SEM specimen, 80 millimeters long. We took a high alloy steel, IC304, black painted in the region where we make our lock-in thermography. Here you see the pin for the DC potential drop measurement. This is built in our machine with fixed grips, so we don't have any bending forces, and we can make our we made our experiments with a frequency of 20 Hertz and kind of fully reversed loading. We made constant force and constant stress intensity experiments, and here the constant stress intensity experiments are the more interesting because we kept the stress intensity as well, Kmax as well as delta K constant, so that we achieve a constant crack propagation rate during our experiments, and so the conditions at the crack tip should be the same over the complete experiment. Logging thermography, I think, I make it very short. You measure a temperature signal due to the force, and you make a lock-in filtering to get off the noise, and then you can make an amplitude image, just define the amplitude, the temperature change within one cycle, and as Professor Sakagami showed, you can use it to F criterion for the dissipated energies. Here you get the elastic stress with a loading frequency, and with a double of the loading frequency, you get the dissipated energies due to the plastic deformation. And you get two pictures, E-amplitude pictures, where you see the elastic stresses in front of the crack tip. Here is the notch, then you have the crack, and in front of the crack tip you get the elastic stress field, and you get in the D-amplitude the dissipated energy, and here is very interesting, you get dissipated energy along the crack path and in front of the crack tip. And the crack tip is located somewhere here. We've seen in the presentation before that's not so easy to find. These pictures were all collected with the software Altair-LE, and there's no motion compensation in these pictures because we don't need it for this evaluation. Let's go to the Peltier-Sensor. This Peltier-Sensor, which was introduced by Oleg, consists on a copper plate, and on the copper plate we mounted a Peltier element, again the copper plate, and the second Peltier element. With the Peltier element below, is just for cooling, for making a constant temperature in this copper plate in between the two Peltier elements. The specimen or the sensor is pressed against the specimen by use of a little bit of thermal paste to enhance the conductivity between the sensor and the specimen. And then we get, when the specimen changes the temperature due to the mechanical loading, we get a heat flow through the first Peltier element we use for measuring, and we get a measurement signal, we get a current, and then we use a resistor to get a voltage which we can measure with the electronics of the testing machine. So we can incorporate this sensor completely into the control electronics and the control software of the testing machine. That's a big advantage. We don't have two separated systems like in the case of the thermograph. For calibration of this sensor, it's very easy. We made a specimen out of plastic, incorporated a resistor, a flat resistor into the specimen, pressed it against our sensor, conducted a current through this resistor, and so we know exactly the power coming from the resistor to the measurement Peltier, and so we can calibrate this to a heat flow, and that's all. This sensor is assembled in our testing machine. Here you see the two grips, and here behind the sensor a Peltier element with a size of 10 to 10 millimeters. When the specimen is built in, you see the sensor is behind the specimen, and so we can measure from one side with thermography and from the other side with the Peltier-Sensor. And so we can compare both measurements within one experiment. This is a result you get from a heat flow measurement experiment with a constant force of 8 kilonewton, cyclic loading with 20 Hertz, and you see the heat flow as a function of the cycle number. We have at the beginning a starting effect because you get a heating of the specimen. Afterwards we have a kind of plateau region where we say, okay, we have there crack initiation and short crack propagation, and the increase at the end belongs to the long crack propagation in the specimen. We can compare that with the potential drop, and here you see the same. You see here this plateau region, a slight increase due to the short crack propagation, and a big increase due to the long crack propagation. To make a comparison with the thermography, we made a simple evaluation. We took our images and put on a square with the same size and the same position as the Peltier element from the backside, and we made just an average of all amplitude values within this square. And so we say we can measure the same with both methods, and so we can compare it easily. Here now the experiment with 8 kilonewtons. At first the E amplitude, that means elastic stresses, with over the cycle numbers in this experiment, and you see also plateau region and a steep increase due to the long crack propagation. Nearly the same you have in the D amplitude, that means the dissipated energies. You see also plateau and a steep increase at the end due to long crack propagation. The same you also see with the specimen temperature, also measured by thermographic methods, and again the same in the heat flow measurement. So you see in all that nearly the same. And as said before, more interesting is the Kmax in constant experiments, and now I come to that. And here you see the E amplitude image. The E amplitude is decreasing with the crack length due to decreasing force you have to apply to achieve a constant crack, stress intensity at the crack. The D amplitude is rising with the crack length. We don't know why, but that's the measured value within this square. Specimen temperature decreasing during the experiment, and also the heat flow measured by the Peltier element also decreasing in this experiment. And now we wanted to compare these two methods, and I will start with the E amplitude. And the E amplitude, when we take the E amplitude, thermoelastic stress measurement, when we draw the E amplitude values over the force, we get a linear dependence due to the thermoelastic effect. That's all. The same we should see also in the with the Peltier-Sensor, but as you can see, when we draw the force and the heat flow range, that means the difference between the maximum value and the minimum value within one cycle, we get this chaotic curves, I would say. We just have scatter. We are not able to measure a thermoelastic effect at higher frequencies, but if we go to a low frequency of 0.2 Hz, we can also measure thermoelastic effect with this Peltier-Sensor. And this is due to the response characteristics of the sensor. It's not so fast as the thermographic measurement. The second one is the heat flow drawn against the specimen temperature. And here you can see with the Peltier-Sensor, you just measure the temperature of the specimen. That's all. And it's just calibrated to the heat flow so that you get a value in watt and not in degrees Celsius. And now we come to the problem of this complete measurement. The heat flow measurement, we take a specimen with a crack inside and we get dissipated energy at the crack tip. And this dissipated energy flows into our specimen. We get heat conductivity within the specimen, but our Peltier element covers only this region. And so we have two different cases we have to look on. We have a heat input per cycle in the crack tip, and this is greater than the heat loss. Then we get a specimen temperature rising and we get a heat flow that is rising. Is it the opposite? Input lower than the heat loss, the specimen temperature and the heat flow decreases. And so we have a problem that we have to correct our heat flow measurements, and there we at the moment are working on a correction based on the work of Professor Meninghetti. We make just some experiments with interrupt, and we measure the cooling of the specimen during this interrupt, and the heat flow decreases, specimen cools down, and we can correct our heat flow measurements with this heat loss we have within these within each cycle. And the heat flow, the corrective value is the heat we dissipate per cycle and the heat we lose by cooling down within a time period. So let me summarize this. Logging, thermography and heat flow measurements, very interesting for playing with our propagation experiments. The Peltier-Sensor is simple, easy, well integrated in our testing machine. A very nice feature to do that, but we have the problem for that we have to correct these values due to the heat loss of radiation and heat flow within the specimen. But with the thermography we can make space-resolved measurements, and what we've seen before, we can distinguish between effects in tension and compression, where we can't do with our Peltier-Sensor. But we're still working on that, and we also enhance our specimen preparation for the thermographic measurements. Quantitative measurements are a little bit difficult in this case, but we're still working on that, and I hope that I can present next time some more results from our before we went. Thank you very much for your attention.